Alrighty then, happy Halloween and Tuesday at the same time. I had a plan for today, but that was before I left my laptop where I'm staying, and so that translated into a little adventure on I-75 when there was 4 lanes of hold-up traffic. So the computer hasn't been acting very well today, so I can blame everything on it. I'm not sure the graphics are going to work well, and what I had for a plan may not work too well, so bear with me a little bit. Conceptually, what I'd like to do today is spend a little more time than normal reviewing the assignment you did. Bottom line on that is everybody had a good description of the behavior of the pattern, but we didn't have quite the synthesis we had. What does it all mean? Why of it? Which was half the exercise. So I want to walk through that because ultimately I want to use a different model, but for a more specific problem for today's exercise. And so there's a little bit of scatteredness going around here, so hang tough. And one of the things too is what you see on this may not exactly be on the PDF that's on if you uploaded it. So the first thing that's happening is I wanted to go through that exercise, but that website's not loading for me today. So I'm going to do it on the chalkboard the old-fashioned way. And what we did in the excuse me. I'm going to spend time commenting on this. Then we're going to go back to methane. And then I'm going to talk a little bit about where energy comes from because that has a lot to do with fossil fuels. Go back to fossil fuels. Then I'm going to kind of take a diversion. I'm going to talk about real long prediction of ice sheets just as an example of why we might want to go into deeper time. And then look at that. I don't know what that says. Look into something or another. So that's where we are with that. To get to this first comment on the homework, then I just put this up. It's to emphasize everybody did really good on the bang, 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 bang on one pointer. Some of you were a little bit better than others. You would write out values. You say that the graph trended and it increased. Yes, one of the better ways to do that would say, well, it went from 10 to 12, or put some numbers in there. But that's not the real issue. The real issue is what do we do with that kind of information? So if we remember, these 3 things were to look at particular pools with no carbon usage. So there was 3 cases. No fossil fuels, right? Case 2 was if you used fossil fuels at a certain rate, if there was a flux of a certain rate, and it was tens, and I forget the exact units, right? And then case 3 was if you had the double of that. And we looked at that thing over several hundred, what was it, 150 years or something like that. So you did exactly the same thing, and I asked you to look at 2 pools. And one of the pools was the fossil fuel pool. One of the pools was the atmosphere, and another one was the ocean, right? And remember that the pools have 2 things. They have a size associated with them, and this one's 32, a bunch of numbers. This one was 750. And this one had, I forget the exact number they had in here, 7,000 maybe? I'm not sure about that. And there's another part of this. It's the flux between them. In other words, these fossil fuels ended up getting into the atmosphere. But then the atmosphere actually put that into the oceans, and there's a balance between this. So this is the bathtubs that we've been playing with. And we changed the size of the bathtub. We changed the size, but you were tracking the water level. We changed the size of the hose going in or out, and we wanted to see how long it would take to come back or how it would happen over, I think it was the 500 years. This is a very typical modeling exercise in the sense that the model didn't actually talk about human use of CO2 or fossil fuels. It just said we have a property, we have something, we're going to transfer it into someplace else, we're going to transfer that into somewhere else. how does this behave at the very simplest level? There's some math behind it, but not much in this one. It's basically just algebra. And we're still going to get those exponential and funky relationships. This doesn't tell us a thing about why it's happening. What we do with a modeling exercise is we look at the results and then we see, to some extent, why or how things interact. So if I look at case 1, and I look at the fossil fuel thing, the fossil fuel stayed basically the same level all the time. Why was that? Didn't change.
Because it is constant, whatever the case 2 and 3 were.
The pool, the total amount of of fossil fuels, which is a big number, wasn't being exploited. It wasn't leaving that pool. And so the rate of the fossil fuels was 0, so the fossil fuel stayed exactly the same size. The next pool that we looked at in fossil fuel, this is for 0, this is for 10, this is for 20, right? And you could have slid this to any exact numbers, I just did it. What was the property of that one? Remember? It changed. It wasn't flat. So what would happen if I start using this pool? In other words, I'm dishing it out. I don't know where it's going yet, but I'm dishing it out at a certain rate. What's going to happen to it? I start with 7,000 marbles, and I start giving 10 marbles an hour away. What are the number of marbles that I have left? That's what we're asking. Is it going to get bigger or smaller? Stay the same? Well, if I've taken the marbles away, somebody's getting bigger, but not me. My marbles are going someplace else, so that's going to be basically a linear trend down, right? Now, if I gave away 20 marbles every day or every hour, what's going to happen to the trend of my pool of carbon? Gentleman in the blue.
You're going to run out quicker.
Well, one of the things is going to be a steeper slope, right? I'm going to give away more marbles per hour. Now, I may or may not run out of marbles, but that's what's going to effectively, if I'm going to run out of marbles when it gets to 0. So there is a finite time. I could have run out of marbles giving away 10 also. It was just taking twice as long. So part of this thing, and this time is always on the x-axis. So I'm looking at the evolution of my marbles or the size of the pool or whatever over time, everything. All right, so that was made sense here. So over here, I think is going to work out better than showing you the model, if you can read the diagram. So here, what happens to the pool of the atmosphere in the case where I'm not adding the lady with in the black shirt today, the very festive black. What's going to happen to this pool of that as what's going on at this time in this case? Am I move? It's going to stay the same because I'm not doing anything with this. I'm not taking any water into this. So this level stays the same. Okay. And then what if I start giving my 10 marbles away? What's going to happen to the amount in the atmosphere? Go ahead. Yeah. It's going to increase at some amount. So the 10 marbles keep going down. So does it just forever go up and up? Kind of, as you think of it. But does it really? Here's where there's another pool. Because there's some sort of arrow going this way. Well, there's also an arrow here. So now I've got the bathtub with an in and an out. And maybe that's getting absorbed into something called the pool of the oceans. And in this case, it is. And does anybody remember what it looks like? A lot of you had the graph of the thing. The pool of the ocean, this one stayed the same because the ocean, it's a much bigger number. But I'm not transferring anything. So it has to stay the same. Now, am I transferring, I might be transferring 10 here, but does that mean I'm transferring 10 over here? No, not necessarily. And I got to remember that this guy started out with 32,000 marbles, so 10 isn't going to make a big difference to him, right? So the atmosphere is going to translate to this, and it's going to go up, but at a slower rate than this, because this is only dealing with 750 marbles, and 10 is a big deal. So this goes up. This is also going to go up, but at a slower rate. All right, now, lady with the green today, green water bottle. I'm going to jump to the case where I burn up the most carbon, or I take the most marbles away, and I'm going to burn out the carbon, not at the end of the simulation. What's going to be the atmospheric concentration? This is actually one of the more interesting ones. Remember what that looked like? No, okay. Anybody remember what that looks like? Somebody described it very well. It's the wonky curve or something. Was that you that used those terms?
I don't know about that,
But okay, but it's the most complex graph we had. Why? What does it show?
because it will go up kind of exponentially, but then it will, as soon as you run out of carbon or fossil fuels, it will drop off again.
And then there's a little subtlety here. But yeah, there's no more fossil fuels going in because I've hit zero. I've run out of marbles. It's going to go down. And where is it going to go down? It's going back into the ocean, right? Now, is it going to make a big deal? So this dumped this in and jumped it up a lot. But again, the ocean is so big that we're going to see the effect, but not really that much, right? And I don't think this is a straight line. Do you remember what it was? It's slightly tilted. The point is that this is showing a lot more marbles to start with, and the rates coming in attenuate that. So I worked through these things, and so the analysis then becomes describing all 9 of them. And that was easy. We got that. Now, what catches our eye as being funky? Well, this one just doesn't make sense at first pass. Everything else is kind of straight or exponential. Well, the first clue is that's when we ran out of marbles or fossil fuels. So it was going up, going up, going up, because it was getting into the atmosphere, but then it purges itself out of the atmosphere. So that tells me that this thing worked away steadily and then drew this down. Now it also is going to draw it down in an exponential. So the resulting line here, which I don't think is a straight line, but it's a small change. That's the whole essence. And now the y is because the rates, the fluxes, the size of the marble transfer differ, and the respective pools are different. And in this case, I ran out of one of the pools, and so that effect propagates, but it only propagated when I went to 20. If you went back in and you wanted to say, how long would it take me to keep keep fossil fuels in here? I want to keep doing fossil fuels at some rate. You could move the slider back, and you'd see this thing keeps going up at all times, and it never comes back out of here, because I can change this flux to make this do anything I want. We're going to do the same exercise with what's called the sluggulator. This is setting up a concept, though. What happens is instead of slowly leap this, we dump it in as a bucket. The bucket analog will come in, is the big deal for today. Questions before we go any further? Can you understand those graphics? They're really exquisitely written, I know, but I don't have a big piece of chalk. Okay, let's get out of that. And this is, so we're going to play with methane a little bit today, and what we're going to find out is that there's two curves here, a red and a blue one, and they do something a little bit differently, but you can see they're related. So we'll get into it a little bit deeper, exactly how that might be. Before we do that, we want to go back to the concept of CO2 in the atmosphere and why that's a big deal. And a lot of you had human activity in this model. Well, there's no humans in this model. There's no math in there that has an equation or variable for humans. Ultimately, yes, it's an activity that we're doing, but I could, and biomass burning would have been the other one. And we seem to think that this is a new thing, but if we look at on the influence of carbonic acid, CO2, and air upon the temperature of the ground, 1896, it's been known for over 100 years. So the concept's not brand new. This guy is a famous chemist, and he recognized it. And this is sort of the blurb of this. This is where it was, the Philosophical Magazine of the Journal of Science, blah, 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 1896. This is all of the garbage you can't read, and this is if you wanted to read it. And it says basically the first to quantify the contribution of carbon dioxide to the greenhouse effect, which we know what that is. It's a radiative forcing. All right, so that's nice. That's historical perspective. Where does all this CO2 come from? Why do we have a CO2 flux? Because we need energy. We, as a society, demand energy. And historically, the easiest energy you get at was fossil fuels. You can dig in the ground and get out coal. You can drill in the ground and pump it out and get oil. You can refine the oil and make gas. And so it's interesting to look at how much energy we consume as a, this is US only, in a year. And this is a big set of numbers, but pie diagrams get it to the point. And this diagram gets updated every year. And the point is, what we may think of as fossil fuels, coal, 10% of the energy supplied to the United States. Natural gas is 33%. Petroleum is 36%. The nuclear is about 8%. And then what we think of as the renewable energies are only 13% of the total energy contribution. So it's the one that gets the most press and the one that we think we're going to do something with. But if we add these numbers up, 33, 36, that gives me 69. And 8, 79% of our energy comes from what? Those three things collectively we call the fossil fuels. So you think we're going to give up 80% of our energy in the next week, next year, in your lifetime? This is part of the problem that's really pervasive here. If we get into the renewables, and if you saw this graph for years, we find out there's some interesting things. Biomass, collectively. 15% of us burn wood. Biofuels are those ones generated from excess fat from French fries. And biomass burning is little pieces of wood that are left over when you cut down a bunch of trees and you throw it in a hopper. Wind is now 30% of the renewables, which is a big deal compared to what it was 10 years ago. Dams are an important source of it, but they've been a source of electricity for a long time. Solar's coming online, and geothermal is a small percentage here. So these are kind of these are round numbers, but they're all pieces of this 13%. So we can't go to a renewable energy resource next week, nor next year. If we think about this, just to bury it long, this is a diagram of there's where all the energy comes from: petroleum, natural gas, renewables, coal, and they stack them in order, and then nuclear. So basically, this is the energy input. Well, where do we use it? And so what we want to talk about over here is it's used in transportation, it's used in industry, it's used in residence, it's used in commercial. So it's diffuse usage, and what you do is you trace an arrow. You trace an arrow, and then you can't read those numbers, but you trace an arrow, and that percentage of it goes to that. So the petroleum, some of it goes to here, some of it goes to there, some of it goes to there. These are actually pretty big numbers. This one's small numbers, doesn't matter. There's a pattern to it. And so basically you see that all of these contribute to all of those sectors. Natural gas contributes to all of those sectors. Renewable energy contributes to all of those sectors. Coal, it misses one sector. We don't use a lot of coal for transportation anymore. We did when we had railroad cars that ran by coal. We don't anymore. And nuclear isn't used much for transportation or industry or anything. Now, there's a black box down here. And the black box says something about the electric power sector. Energy and electricity are two different beasts. Energy is one form of energy. Electricity is actually a way to transmit the energy from wherever it's made to wherever it's used. So we have to think about a part of energy that gets diverted down into here and then comes back out to these things. So we'll see that, you know, electricity is used in transport these days, in everything. But energy is just a way to transmit the energy. Excuse me, electricity is the only way to transmit the energy. There's two colors here, and I don't expect you to read the writing, but it's actually, this is pretty good sized hunk. This much electricity is the equivalent of the total renewable coal and nuclear generation capacities. That's not quite a third. So a third of our energy is moved around by electricity. Great. Two colored boxes. The arrows don't come out of one of those boxes. The arrows all come out of one box. If you read the fine print here, it says electrical system energy losses. It's a big box. Electricity does not transmit energy 100%. There's enormous losses in it, which we don't realize, but that's a big box. In other words, we're using sort of all of the power that we generate by renewable energy, and coal is effectively lost because energy is not effectively. And when you pick up your power adapters and that warmth, that's energy that's using that power to charge up your batteries, but the warmth is energy lost. Likewise, any energy transmitted in lines is lost, some power. And nobody really talks about it being, this is a fancy term for energy, BTUs. And this is in a really big number, and you could talk about 35 of these things for petroleum, or you could talk about 33 for this. Well, we lose 24 of those units. That's a lot. I keep telling people in this class, if you really want to save the world, cut this down from 24% to 20%. We'd have all the power we wanted. Not as simple. I mean, people are working on it, obviously. Questions on energy generation or where it goes in society? Fossil fuels are still there. They will be forever. Now, since we're committed to fossil fuels, it's germane to ask, and we know that there's only a finite pool of fossil fuels. And we saw the point that there's the Hubble curve of of at least oil and probably natural gas and coal, but they're all slightly different. It might germane us to think about how much some of these numbers, and this is mostly just think about, you know, something about millions of barrels of oil. It's 36% of our energy. That means how many gallons, millions of barrels of oil a year, and then you get to these big numbers. And now we get to something like a gigaton. All right? And then we get to the sort of the, how much is from the US? Well, it's 0.01 gigatons. Well, if we get back to these things, these are in gigatons. So now all of a sudden we have some idea to think about what the US contribution to these things are. And the total value in a global sense is 36 gigatons. That doesn't seem like quite the right ratio to me, but it is what's on the slide, so it must be right. So those are sort of rates. At these rates, though, at so many million barrels, you're going to run out of oil at some point. And then if you run out of oil, conceptually, you're going to end up reducing the fossil fuel contribution of oil, or you're going to run out of natural gas, or you're going to run out of coal. And we're cleaning up coal now because it's a messy thing. We're effectively going to run out of this. So the rhetorical question becomes, if I take all the fossil fuel resources that I know and I dump them into the atmosphere overnight, hypothetically, how long will the CO2, elevated CO2 being in the atmosphere? 5 years, 500 years, 5,000 years? That's the point of this exercise. And we can do it. So this is called the slug. This is dumping the bucket into the hopper. And the assumption that at some point the emissions have to drop, and we manage it, or because we've decided to curtail the use of fossil fuels, or not, or we run out of them. The atmosphere is only a temporary sink in all of this. It's the first receptor. But ultimately, the ocean is where the big action is, the long-term action. So here are some hypothetical models, and this is the year of between 1900 to, and this is current. It's a little bit dated now, but for a couple hundred years out, 300 years out in the future. And so what we see in this particular set of pretty graphs is how much emissions in this gigaton per year, and this is globally, and this is sort of where we are today, and these are projections based on different fossil uses. But they basically all have the same curve. They're going to die off in the future. All right, so the emissions go into the atmosphere. Well, that's great. So what's the atmosphere going to do? Well, here's the curve of the atmosphere, and here's, it's a bit dated again, but here's the steep peak of CO2, and right now we're right there. And so you can't tell if we're going to be in a blue line or the red line. These are different scenarios. We're in the red right now. But as I drop that off, gentleman in the Bearcats hat, if I drop these off, what does this reflect?
It seems like flattened out a little bit.
They flatten out. Now why though? We just answered that over here a minute ago, but they flatten out each respective color. They eventually do it. But why would they flatten out? That's in this graph, we're not exactly cutting it back to zero, are we? But we're getting down to low numbers, so these numbers aren't going to go up anymore. They're going to stabilize. Well, this is 200 years in the future, and they might change, but it's going to be out here someplace. And that's what we want to know, what that someplace is, rhetorically, more than anything. So the levels will stabilize, and then the oceans are sort of the long-term catch-all. Similar information in a slightly different fashion. This goes back to our conceptual model here. And this is about diffusion and the exponential movement of stuff and the fact that these are exponential decay curves. And so there's a concept called residence time, slightly different. If I take a particular model of CO2 and I dump it in the atmosphere, statistically, how long does it stay there before it gets sucked out from the atmosphere into one of these places? So that's the residence time. And they have 100% of it stays in the atmosphere, 80%, 40%, whatever, 300 years out here. And basically, these are political decisions, but basically they come down and stabilize back here at 20%. Even after 300 years, the new equilibrium's 20% of the stuff. If you want to ask how much, how do you get it back to what it really was in the atmosphere, you have to wait longer. This graph is 10,000 years out into the future. And you see that it comes down fast, which is a blow up of this. the first couple hundred years, but then it asymptotics. And so you have to wait something about 10,000 years to get back down to 10% of it remaining in the atmosphere. It's an elevated percentage, higher than it was. If we stop dumping it in tomorrow, this would happen fast in 50 or 100 years, and then the effects keep going on and on and on, because the atmosphere, there's not enough drive, if you will, there's not enough gradient to get it out of the atmosphere. Gentleman way in the back, question on that. I know you have a question on that. Blue cup, the blue cuppy thing, whatever they are. Can you explain to somebody you're going to go trick-or-treating tonight and you're going to say, you better give me a treat or I'm going to explain this graph to you, right? That would be a good trick-or-treat, right? All right, so how would you, and they called your bluff, so you didn't get a candy bar. And now you've got to explain it.
So if we were to stop releasing CO2 into the atmosphere, the amount of CO2 in the atmosphere would decrease after.
Yeah, we know it's going to decrease because the ocean's going to keep sucking it up, right? The net's into the ocean, right? And then pick one of these things. They're slightly different graphs, but because one's 300 years and one's 1,000. How about this one for 300 years? It's easier to register than 10,000. How much of that CO2 is still going to be there after 300 years?
20%.
Sort of 20%. Going to come out fast and decay, and these are different scenarios, and we don't need to worry about the different scenarios, but they all converge. But you're stuck with 300 years for, I don't know how 300 years is, I don't know, 5 or 6 generations? I don't know how long a generation is. Okay, anything else to add to this? All right. We want to explore the oceans in a more detail. So we're going to use a second model that has the oceans as 2 parts rather than 1 part. And it also has a few more knobs to twig. The last one we only had the ocean as 1 part. Here's a simple model, and one of the advantages, and it's the slug, it's dump a bucket in and see how it goes. This model is set up to put 2 different slugs in, one of them called CO2 and one of them called methane, CH4. They have different properties. One of them doesn't go away very fast, one of them goes away pretty fast, but it turns into CO2. And so we can think about the methane and we can see what happens to it and how effective it all was. So what does this model look like? Let's see if my internet's working on this today. Maybe it is and maybe it isn't. So I think I made a brief statement yesterday that this is from the University of Chicago, a guy named David Archer, and he does it. So here's the landing page, basically, of a variety of different things that you could talk about that he will do for you or will calculate for you. And methane, and then carbon on the long geologic time scales, millions of years, methane per se, slugulator, the peak curve of the oil, and then a scenario of different developments. So most of these are a little bit, these particularly are more technical. We want to have gotten into here. Yes, we don't want to do that. So we want to go to the slugulator and be done with it. So the basic setup of this, if you can open it up, you might want to at this point, but I'm just setting this up for the exercise. There are 2 graphs, and more importantly, They're inputs. All of these things are numbers that you can put in, knobs you can change. This gives you some numbers to go along with the pretty graphs. There's two drop-down boxes there. You can change what the graphs are of. The other drop-down box that's not so obvious is time. So you can run this for 100 years, or you can run it for 10 years, 50 years, up to 1,000,000 years. So you can mess around with the time, and you can see the same graph. This is 10,000 years. It doesn't look like anything's going on because all of the action was going on in the first century, basically. But if you come back to 100 years, whatever these graphs are, they're happening in the first 50 years. Now, these drop-down boxes are, this one is basically, we only want the concentrations. We don't want the radiative forcing, the equilibrium temperature, the surface temperature anomaly. That isn't too good. You're welcome to explore them, but for the sake of this exercise, we just want the surface temperature on this one. So this is the setup that we want. So here's temperature changes, and here's the CO2, here's the concentrations, and we see a blue and we see a red. And I'm going to zoom in on that just for a minute. The lady, I'm looking through these two gentlemen, and I'm going to ask you to describe the difference between the blue and the red curve, please, broadly speaking. It goes up like mad, and then it keeps going, though, right? Okay, and the red curve? Goes up for that, and then it decays slowly here, right? Okay, so it turns out this is CO2, this is methane. We're only talking about 30 years or something here. So this is what would be a model that's your lifetime. How can we mess around with it? How can we learn anything? Well, here's where we put in what they call the spike or the slug or the bucket. And I've just put in a gigaton, and I've put in a gigaton of each of these. Okay? Pick a number between 1 and 100 or 200. For CO2 or for methane? So I'm going to put the number 20 in here because that's 20 gigatons of methane, excuse me, of CO2. The dump for one day, I just dumped a bunch of it in here. How is your graph different now? Dumped it in a couple years, it stayed at that same level. Okay, what about the temperature, the effective temperature? This one peaks down and the other one goes stabilizes, and that's temperature, right? That's the global surface temperature. So how much did the surface temperature go up? Again, I know you can't read these numbers, but it went up. Tell me when to stop, and I'll read you a number. How much did the temperature go up because of methane, right? That number looks like 1 degree, basically, I think. All right, so now we can sort of see, and this model's more sophisticated, there's more knobs to turn. If you don't turn the right ones, your numbers are going to be a little screwball. All right? Gentleman in the black hair back there. Do you want to jack up methane? Or how about methane? We'll go back, we'll reset the CO2 to the same thing. Now, you want to dump a slug of carbon dioxide in the atmosphere. What do you want to do? How long do you want it to? Let's go for 100 years for chuckles. But now I want to dump some CO2 in it. how long do you want to, within the next 100 years, you want to track the CO2? Just by doing nothing, it sort of stays the same, right? All right, now if I dump that slug right in, a bigger slug, pick the size, please, give me a number. 40. You're really conservative here. I mean, 40, let's just take a minute here. Take a minute here. Okay, 40 is sort of what the global average is today. So it's not going to really make that much, that's the slug that we put in this year. How long is it going to be before it clears itself out, basically? It's not really a slug since it's at the constant rate. But we'll go with 40 for chuckle. All right, I'm going to go back to the slug because you described to me what the normal conditions are for 100 years. And you're only dealing with CO2, so the methane should be 0, right? So what's the CO2, the blue line, doing? So not much change in 100 years, right? What about the temperature as a result of it? Big increase up front because of the radiative forcing, but then it doesn't change much. Okay, now I'm going to dump my, you said 40? That doesn't look right. Okay, it was right. Okay. Hard to see much difference, isn't it? Because you can't see the scale. But the same pattern. It doesn't really make 40, since that's the normal thing. That's what. Now, what's the implication of that? If we keep putting 40 in this year, 40 in next year, 40 in next year, some of it goes away, some of it goes away, some of it goes away. But is the temperature ever going to go down? No, because everything that goes away is being replaced. So we're in a one-for-one thing with an elevated temperature. That's interesting. All right. Oh, there's our climate sensitivity numbers from way back. We could jack that around to 3 or 4 or 5. And then the life expectancy of the radiative forcing. The other thing in here is interesting is that how fast the oceans churn around. And 1,000 years is a good number for us. Want to do one more of these? What number would you like to do, methane or CO2 as a dump it into the atmosphere?
Methane, let's go with,
Excuse me, methane?
yeah,
52? 52? Seems like a low number, but let's try it.
No, it's methane.
Methane, excuse me, yes, thank you. That's sort of our base conditions, and now we're going to 52. And what's happening here? Here's the concentrations. The methane goes up and it comes out because it oxidizes in the atmosphere. So our 52 came back to a baseline, sort of, well, that's 50 years, so 30 years, right? What about the temperature? Did the temperature come back to normal in 30 years? Red is the methane. Temperature, effective amount of temperature contribution spiked and came back down, right? And then what happens to it?
Just like it approached to the original temperature. But
Yeah.
not.
It effectively burns out and it doesn't have any contribution. What happens to the CO2? We didn't put any CO2 in, but the CO2 contribution to temperature, the CO2 went up. Why did the CO2 go up? We didn't put any in. Where'd the CO2 come from in this model and in the real world?
Come from the we burn that methane, so it creates CO2.
Cha-ching. The burning of the methane makes one of the byproducts is CO2. So to get rid of the methane, we added CO2. So they talk about methane as being a more potent greenhouse gas than CO2. And on some time scales that's true. And here's an example of it. CO2 is not doing much here as a contribution to temperature, but CO2 is doing a big thing. But they talk about it like over 70 years. And the reason they talk about it over 70 years is that's when it burns out. So then you're still stuck with the increased temperature from CO2, even though there's no methane there. Whew. Anybody want to see any more examples on this before I turn you loose? With the questions are much simpler than they were the other day. Well, they're still analysis questions. All right, I'm going to take a diversion into why, if not, I'll take a diversion into why we might care. So now we've gone through the simulator, and we're going to go back to predictions. You're going to make simple predictions. What I wanted to do is think about the longer term geologic timescales of the behavior of the Antarctic ice sheet because of longer term burning of fossil fuels. So there's the southern ice mass. What does the CO2 at higher levels look like? This is an extreme case because we want to burn out all of the CO2, and we're talking about a 10,000 year time frame here. And why do I care about that particular hunk of ice? Because over 10,000 years, you got time to melt it. And I don't know why this thing is not, it's misbehaving entirely. Okay, so, and this is a few years old, but there was a study several years ago that did exactly that. Let's presume that we're going to dump all the CO2 up in the atmosphere, and then let's make a much fancier model than the one you're going to use, but let's see what's going to happen. Then let's translate that heat to melting of the ice sheet. And so, oh, we can drown it. You know, the pizzazzy thing is, in Scientific American no less, can drown you out much sooner than you think. And so this is the popular press release on that. Well, how fast is soon? Melting of just Antarctica. And here, if you read the abstract of the technical paper, they talk about blah, blah, blah. We use a particular ice sheet model. They're going to take a model of CO2 concentrations, input it into an atmospheric model to see what the temperature is, and put that into an ice sheet model to see how the ice sheet responds. We saw in simulations that burning the currently available fossil fuel resources, burn it all, burn baby burn, is sufficient to eliminate the ice sheet. So their contention, if you believe that statement, is that as we continue to use fossil fuels, because it's not going away, the effect's not going away next week, the ice sheet will disappear. I like that ice sheet. With that big number of these gigatons projected almost ice-free. Oh, now they've waffled. We're going to eliminate it. Now it's almost ice-free. And then, not only that, we're going to get something about the rates of return of the water that's stored above that. So back to our sea level problem. And we're going to talk about 3 meters per century for the first 1,000 years. We've been worried about a meter, and now we want to go to 3 meters per century. Okay, so this is a model, this is a prediction. Result in the threshold trace that's threatening in its entirely, and because the associated sea level rise, because there's so much stored water there, it's bigger than anything else. So this is a real long-term prediction. Nobody that's alive today is going to be around to see it, so fine. I would argue that basically this is it was an experiment. It's an interesting concept. It's a good extreme case concept. The what if, and that's exactly what you do with models. The details will be argued off into the night. But whether it's 10,000 years or 9,000 years really doesn't matter. And the 58 meters, I think we've talked about this a little bit before with sea level. Florida's gone. So that's nice. that one ice sheet, this is Greenland, this is this is that, and 58 meters is this, well, basically it's these two. So we get Florida and we start getting some of that. These are the graphs from their paper. So these are much more technically precise or accurate or reasonable, but they're exactly the same concept. And they talk about the year, they talk about the year 2000, or that we're in the year 10,000 down the road. And here's the different models. They dump the total amount of carbon, of the load of carbon in real fast, and then it burns out. Same behavior that we saw. Stretch the graph out, looks like more of a spike. And then we see a set of curves with a decrease there, and the temperatures spike. Source, CO2, this, exactly the same setup we're talking about. But the temperatures stay up there. Now they come back down for these, the blues and the yellows, which are the smaller amounts, but for the bigger amounts, we're toast. The atmosphere is high for the duration. So they took this and then they used this more complex model, and I'll take a sidetrack on the sidetrack here. Part of this has to do with the transfer from not just the atmosphere to the oceans to the deeper oceans, and then hence in here. This is the bottleneck. We can saturate the oceans, got to get rid of it sometime. So as a derivative of dumping CO2, change the chemistry of the atmosphere, change the temperature pattern, melt the ice sheet. And we see that most of the action of the ice sheet's in the first couple thousand years. And then it keeps going. Fine. And in a pretty map, this is what it would look like. Today, 500 gigatons, 1,000 gigatons, 1,500, and this is the almost. They're modeled in several thousand years. That's what it would look like after 10,000 years. All right, fine. That's a reason to think about using this model. Oh, and then they convert it to the rise in sea level. And the real rapid sea levels don't kick off for a few hundred years, so we're safe. This mechanism is not going to do us in. All right, that repeats the same thing. We're back to this sluggulator. We're going to run methane. We're going to do the exercise. And I think this is all kind of just trying to explain what we've talked about. Anybody have any questions on the sluggulator before I give you the assignment? There's the assignment. We're going to get out of here for Halloween early? Is that the idea? Yeah, sounds good to me. All right, questions? If you model, if I ask you to set up the 269 in the sluggulator into the CO2 category, you're going to run it and you're going to get a fancy curve. What I want you to think about, what's the 269 of methane mean? Where did I come to the 269? And is that a realistic thing, or is that far-fetched? Is that an extreme case? Is that a minimum case? You can get a result, and I'm pressing you at this point to read the result. I'm wondering why we're doing that modeling exercise. And then something about the response of the system. How much is the CO2 spike that will allow, what is a maximum CO2 spike that will allow a return of temperature within 500 years? So we're going to have to play with the numbers a little bit and see what curve matches that particular specification. I'm not reading your faces at all good this morning here. All right, the real thought question. We explained why to do this for sea level rise. Why else would we want to look at something that's an extreme case that's timescales much longer than the political cycle? Because we can burn that fossil fuel out, but it's going to take a couple hundred years to do it. The results, I'm arguing, go down thousands of years. That's okay. Is that just an esoteric exercise, or should we care about it in some way? That's question 3. Ma'am.
So for the first one, are we setting the methane or CO2 to the 269?
Well, I think there's some ambiguity to that, but you could try both of them. But if you, let's try methane for the sake of argument. So run the simulator, keep CO2 introduction, which is actually an artificial construction, right? Because we know we're going to get CO2 anyway. So let's dump the methane in, and let's see just the effects of methane will burn itself out fast. But it turns into CO2, so that's going to elevate things. And then, but this isn't about running the model. This is about why did I pick 269? Seems like kind of an exact number for something arbitrary. Other questions? Happy Halloween. See you Thursday.